See here, this is a characteristic of JFET. This is a characteristic of JFET or output characteristic of JFET. On x-axis we have taken VDS, that is drain to source voltage. Don't write, see here, don't write. On x-axis we are taken VDS, that means drain to source voltage, and on y-axis we are taken drain current, and this characteristic is known as VI characteristic of JFET. Okay, output characteristic, output current versus input voltage. Okay, see here, it is also known as drain characteristic. Why drain characteristic? Because here VDS, that is drain to source voltage, and VGS, that is gate to source voltage, these two voltages are there, and in that VGS, that is drain to, gate to source voltage, control the drain current, hence named as drain characteristic, because drain current is controlled by voltage, hence called as voltage control device. Are you getting this? So it has three regions of operation. Region. It has three regions of operation. Which are those? Cut-off region, saturation region, and ohmic region. Cut-off region, saturation region, and active region. Okay, cut-off region, saturation region, ohmic region. See here, cut-off region. You know that as VGS increases, width of channel reduces down. As you know that this is a suppose this is a P channel or N channel. As VGS increases, gate to source voltage increase. What happen? This depletion layer increase, and depletion layer increase, so reduce down the width of channel. So as with increase in VGS, the width of channel reduced down, and conductivity is also reduced down. At certain voltage called as VGS off, the depletion region touch to each other. And there is no channel. That means channel compact together, and there is no channel. That means ID, drain current is 0. That region is known as cut-off region. So in this region, JFET act as an open switch. That means it not work. It act as open switch. There is no any current flowing through it. It act as a open switch. Then in saturation region, what happen? In saturation region, the VGS is ID is constant. So this is IDS, this is ID. In saturation region, ID remain constant and not change with respect to VDS. ID remain constant, not changes with respect to VDS, is known as saturation region. A region where drain current is constant irrespective of the VDS. As VDS changes, it does not affect the drain current. So that region is known as saturation region. And in saturation region, JFET act as a amplifier. In saturation region, JFET act as a amplifier. Then next, ohmic region. If in ohmic region, the drain current ID variation, in drain current, drain to source voltage VDS. So variation of ID, variation of drain current with respect to variation of variation of VDS. So here in saturation region ID remains constant, but if we are changing the VDS, ID is also changes. So that region is known as ohmic region. When VDS changes, ID changes, that region is known as ohmic region, and in ohmic region ID changes, so it acts as a closed switch. So JFET is further said to be operating as a voltage variable resistance in ohmic resistor. So here JFET acts as a variable resistor here. 1, 2, 3, 4 number of variable resistances are connected to this. Why? Because it acts as a variable resistor. So hence it acts as a closed switch. That means current is directly flowing through this. So here it acts as open switch, and here it acts as a closed switch. And in saturation region it acts as an amplifier. In saturation region it acts as a amplifier. So this is a drain characteristic of JFET. How many students understand this? Please raise your hand. Are you getting this? 100%. So next is transfer characteristic. This characteristic drawn VGS, that is gate to source voltage, with respect to drain current. Here characteristic is drawn between VGS to the ID. VDS, drain to source voltage with respect to ID. Here gate to source voltage with respect to ID. And here IDSS, that is ID saturation. ID saturation when channel is closed. See here, at initially when VGS is equals to VP, when VDS is equals to VP, that is maximum VP, what happened? So ID is equals to 0, that is channel is compact here. So as soon as voltage VGS reduces, what happen? Drain current increase. And when VGS is 0, where is VGS 0? See here, at initially VGS is maximum. Or we can start from here. So at initially ID is 0. Because regions are close to each other, touch to each other, and there is no channel. So ID is 0. So that ID is known as IDSS. So where VGS is equals to 0. What happened? As VGS increases, so this is a VGS. As VGS increases, that means gate to source voltage increase. As gate to source voltage increase, what happen? This depletion region increase and channel reduce down, and as channel reduce down, this current is also reduced down. At certain condition, at certain voltage, what happen? These region are touch to each other and ID is equals to 0. At certain voltage ID is equals to 0, then that voltage is known as VP, that is peak voltage of gate to source supply. So this is a transfer characteristic. Here we are taken on y-axis ID, that is drain current, and on x-axis we are taken gate to source voltage. And if we are taken curvature, it is linearly inversely proportional. Not proper linearly, but slightly in this way. So this is transfer characteristic. This is drain characteristic, this is transfer characteristic. Are you getting this? So draw this. This is very important. From this is the breakdown region, this is saturation region, this is drain region or ohmic region or active region, this is cutoff region. Okay. Are you getting this?